Some things are right in front of us every day. Others we never see at all. Then there's that strange moment, something slips out of sight, and when it shows up again, it's just off. Not obviously broken, not wildly different, but the details don't quite add up. In early 2025, 3IATLAS, an interstellar object, disappeared behind the sun for 40 hours. When astronomers picked it up again, something was off. Its speed was a little wrong. The direction had shifted. Suddenly, the path it followed pointed toward a destination that didn't make sense if it was just drifting through space. This is what happens when you have a blind spot and nobody's looking. Space is full of these blind spots. It's not about lousy telescopes or distracted astronomers. Sometimes the universe just blocks the view. If Earth, the Sun, and some distant object line up just right or just wrong, solar glare wipes out everything. Radio telescopes only hear static from the sun's corona. Optical observatories can't see past the flood of white light. Infrared, forget it. The sun's own heat drowns out everything else. Depending on the angles, an object can disappear for hours, days, maybe even weeks. And in that blackout, anything might happen. There's a name for this: solar conjunction. And honestly, it drives planetary scientists nuts. Agencies plan around it. Mission controllers track it years ahead. When a Mars probe or a deep spacecraft hits conjunction, the whole team goes quiet. No commands go out. No data comes in. Everyone just waits, hoping the onboard computers keep doing their jobs until the sun gets out of the way. It's a scheduled blackout, annoying, unskippable, and locked in by the solar system's design. For 3IATLAS, solar conjunction hit in late January 2025. This was the third confirmed interstellar visitor we tracked, and since its discovery in July 2024, astronomers everywhere had their eyes on it. They measured its speed, mapped its path, tried to squeeze every bit of information out of the faint light it reflected. But as it swung close to the sun, it slipped into the one spot Earth's telescopes couldn't reach. The sun sat right between us and the object. For 40, maybe 60 hours, depending on the observatory, 3IATLAS simply vanished. When it came out the other side, telescopes snapped back onto it. Astronomers did what they always do: compared new data to old predictions. It's just standard practice. The solar system runs on rules Newton figured out ages ago. Gravity pulls, momentum carries. The math usually checks out. If you know where something is and how fast it's going, you can figure out where it'll end up, almost down to the meter. Sure, comets can be messy. Sometimes jets of vapor push them a bit off course, but even that has a pattern. It's unpredictable but not mysterious. This time, though, 3IATLAS didn't fit the math. The numbers weren't crazy, just off. At NASA's Jet Propulsion Lab, orbital dynamics teams ran the calculations again. The object had picked up a touch of speed. Its direction shifted, not by much but enough to notice. When they charted the new trajectory, it pointed somewhere no random object should go. A few researchers quietly shut their office doors and double-checked the math, triple-checked, honestly, before they said a word. But before we dig into what changed, let's rewind. 3IATLAS was already odd before it disappeared behind the sun. The signs had been piling up for months, painting a picture of something that just didn't fit the box we'd put it in. 3IATLAS showed up on July 1, 2025, in pretty much the usual way for comets these days. An automated survey telescope in Chile, part of the ATLAS network, that's the Asteroid Terrestrial Impact Last Alert System, spotted a faint little blur moving against the stars. The computer flagged it. Some software crunched a quick orbit. Then a human astronomer stepped in, checked the data, saw it wasn't one of the usual suspects, and sent out a call for backup. Within 2 days, telescopes across 3 continents had snapped pictures. Give it a week, and there was more than enough data to lock in its path. That's when people really started paying attention. The trajectory wasn't the usual ellipse, not something looping around the sun. It was hyperbolic, moving so fast, not even the sun's gravity could keep it. Just passing through. An interstellar visitor, only the third we've ever actually confirmed after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The astronomy world jumped into high gear. These things are rare, and they're probably the best peek we get into what's out there between the stars, bits of other solar systems, frozen and drifting for who knows how long, now just happening to swing by our neighborhood. Right from the start, 3IATLAS looked like a comet. The James Webb Space Telescope picked up water vapor and carbon dioxide in a thin cloud around the core. Ground-based scopes in Hawaii and Arizona tracked changes in brightness that pointed to a lumpy, spinning object throwing off gas as it warmed up in sunlight. Hubble took pictures showing a soft, hazy coma, the telltale glow you get when sunlight cooks a comet's icy surface. All the classic signs. An interstellar comet, yeah, but still a comet. But then there were the little things. Individually, they just seemed like odd measurements, nothing to write home about. Put them together, though, and the story started to get weird. Take the size. Best guesses put the nucleus somewhere between 440 meters and 5.6 kilometers across. That's either a big building or a small mountain, not exactly a tight estimate. Usually, astronomers figure out a comet's size by checking how much sunlight it reflects compared to how bright it looks, but 3IATLAS defied those calculations. Its brightness suggested a small core, yet the gas it was throwing off pointed to something bigger. The numbers just wouldn't line up. Maybe the surface was way darker than usual, soaking up more light. Maybe it was just way more active for its size. Or maybe the mix of stuff inside was messing with the usual math. Then there was what it was made of. Most comets we see around here are loaded with water ice. That's what steams off when they get close to the sun, creating those big glowing tails. Not this one. The James Webb data showed carbon dioxide, not water, was the main thing coming off 3IATLAS. The CO2 to water ratio was off the charts, way higher than what we see in homegrown comets. That hints at a birth in a much colder place, somewhere around its original star where CO2 could freeze out more easily than water. Different chemistry, different backstory. And then came the polarimetry, basically, looking at how light bounces off the dust. Most comets have a predictable pattern. At certain angles, the light's polarization goes negative, then flips positive as you shift the view. It tells you a lot about the dust grains floating around. But 3IATLAS, its negative polarization branch was way deeper and narrower than anything anyone had ever seen in a comet or asteroid. The light was bouncing off in a way that didn't fit any known material. Maybe the dust grains had weird shapes, or maybe a long soak in cosmic rays had changed the surface during its interstellar journey. Maybe, but honestly, the data just didn't fit the usual boxes. Activity levels threw everyone for a loop. Usually, comets only wake up and start shedding gas when they get pretty close to the sun, about 5 astronomical units away. That's when sunlight gets strong enough to turn water ice straight into vapor. But 3IATLAS didn't play by those rules. It started spewing gas much farther out. Observers picked up signs of water vapor and carbon monoxide well beyond 3 astronomical units, territory that should have been way too cold for this kind of activity. So, what was going on? Maybe the object was loaded with ices that evaporate even in the deep freeze, or maybe something else was pumping out the energy to drive the gas off. The usual thermal models just didn't fit. And then there was its path, strange even before solar conjunction. As 3IATLAS moved closer to the sun, dynamicists all over the US tracked it obsessively, sharpening every prediction with each new observation. Slowly, a strange pattern started to show up, and it made some researchers uneasy. This wasn't just a comet drifting through the solar system on a random route. It was heading straight toward a very specific spot near Jupiter. Jupiter's the heavyweight here, more massive than all the other planets put together. Its gravity rules the outer solar system, corralling asteroids, steering comets, snagging moons, and flinging debris. There's a region around Jupiter called the Hill Sphere, where its gravity overpowers the sun. Anything inside that bubble is under Jupiter's control. The Hill radius, the edge of that sphere, sits about 53 million kilometers from Jupiter's center. Cross that line, and a comet can get trapped into orbit, or a spacecraft can swing by and slingshot off in a new direction. Early on, calculations showed 3IATLAS would pass near Jupiter's Hill radius. No big deal, right? Jupiter's a massive target, and tons of objects cruise through its neighborhood without anything unusual happening. But as data piled up and the predicted course got tighter, the numbers started to get weirdly precise. Not just near the Hill radius, practically hugging it. By December 2024, 6 months before solar conjunction, some dynamicists were quietly pointing out how suspiciously exact the projected intercept was. 53.445 million kilometers, give or take 60,000. That's where it would meet Jupiter in mid-2025. How precise is that? Imagine tossing a dart from New York and landing it through a specific window in Los Angeles, while both you and the building are moving, and you made the throw years ago. The margin for error was tiny, far too small for a natural comet, which should be jostled by unpredictable gas jets and gravity. Still, maybe it was just a coincidence. Space is huge, and odd alignments happen. There was a lot of time left. Comet outgassing could always nudge the object off course. The final approach might not line up nearly as well as these early numbers suggested. Then came solar conjunction, a 40-hour stretch where the comet just vanished from view. Solar conjunction is simple geometry, but it's merciless. As 3IATLAS closed in on the Sun, it lined up almost exactly between Earth and the Sun from our point of view. It wasn't a transit. The object was too small and distant to show up crossing the Sun's face, but it got so close in the sky that sunlight completely drowned it out. Point an optical telescope at it, and you're blinded by scattered sunlight. Radio telescopes just pick up the sun's roar. Even infrared can't help, with the sun's corona washing out any trace of a cold, distant object. Figuring out when an object slips into or out of solar conjunction is just math. You know where Earth is, where the Sun is, and the object's path. Calculate the angles and you can circle the blackout hours on your calendar. For 3IATLAS, that window was expected to last anywhere from 40 to 60 hours, depending on the telescope and the wavelength. Optical telescopes had to wait the longest. Some radio frequencies could sneak a little closer to the sun's glare, but not by much. Astronomers at NASA's Near-Earth Object Coordination Center, the Harvard-Smithsonian Center for Astrophysics, and a bunch of observatories across the Southwest worked together like clockwork. Their plan: track the object as close to conjunction as possible, grab those last clear measurements before the sun's glare wiped everything out, then wait. No one likes waiting, but there's no way around it. The moment the geometry opened up again, they jumped back in, racing to get the first post-conjunction data from the far side. Keck Observatory in Hawaii nailed the last pre-conjunction observations on January 24th. The object was zipping along at about 28.4 kilometers per second relative to the sun. They logged the direction down to the decimal in celestial coordinates. Its coma, basically the hazy cloud around it, was active, but nothing out of the ordinary. Everything matched what the models predicted. Next chance to look. In about 48 hours, on January 26th, when the object would finally pull away from the sun enough for Arizona's infrared telescopes to pick it up again. For those 48 hours, 3IATLAS disappeared. Nobody saw it. No telescope tracked it. It drifted through the most watched solar system ever, and for 2 days it was completely invisible. Perihelion, when it swung closest to the sun, happened during that blackout. That's when solar heating peaks, when any frozen ices on the surface would be boiling off most intensely. No one got to see it. Usually, perihelion is the big show for a comet. Some brighten up like crazy as fresh ice gets exposed. Others can't handle the heat and break apart, scattering pieces in all directions. Sometimes you get an outburst, a huge blast of gas and dust that makes the comet flare dramatically in just a few hours. When the first post-conjunction data rolled in from Lowell Observatory in Arizona, everyone exhaled. The object was still there. No fragments, no weird surge or drop in brightness. The coma looked about the same. For a while, as more data arrived from different observatories, it seemed like just another comet passing perihelion without any trouble. Then the orbital dynamics folks got their hands on the astrometric data, the exact sky positions. They lined up the object's actual location against the predicted path from before conjunction, and the numbers were off. Not wildly off. The thing hadn't taken a wild turn, but different enough to raise eyebrows. The predictions needed tweaking. The velocity was up. Not by much, just about 0.3 meters per second, roughly 1 kilometer per hour. That's the pace of a slow jog. In space, though, objects don't just speed up for no reason. Gravity pulls, momentum carries. If something accelerates, something pushed. The direction shifted too. Against the background stars, its angle of travel had nudged by about 0.02 degrees. That's tiny. You'd barely notice. But over millions of kilometers, even a tiny nudge can move an object hundreds of thousands of kilometers off course. These changes, faster speed, slight shift, are textbook comet behavior during outgassing. When ice on a comet's surface vaporizes, the expanding gas shoots off like a natural rocket, giving the comet a push. Because the comet's nucleus is lumpy and spinning, the jets don't come out evenly, so the whole thing gets nudged in odd directions. Astronomers call this non-gravitational acceleration. It's normal. It's been seen in dozens of comets. So when the JPL team looked over the post-conjunction data for 3IATLAS, the answer seemed obvious. It picked up a bit of non-gravitational acceleration during perihelion. Chalk it up to outgassing. Nothing weird. The models got an update and the observations kept rolling. But then one comet specialist at JPL, who'd followed 3IATLAS since the beginning, decided to dig deeper. Instead of just asking how much the object sped up, she wanted to know which way it got pushed. She mapped out the velocity change, not just the size of it, but the exact direction of the force that acted on 3IATLAS while everyone was blind. The push lined up almost perfectly with the direction needed to fine-tune the approach to Jupiter's Hill radius. Before the conjunction, the predicted intercept was fuzzy, error bars covering a whole range of possible distances from Jupiter's gravitational edge. After the conjunction, after that burst of acceleration, the uncertainty shrank. The trajectory snapped into focus. The new intercept point edged right up to the Hill radius, that invisible line where Jupiter's pull really takes over. She ran the numbers 3 times, hunting for mistakes. The answer stuck. After that, she wondered if a correction like this could happen naturally, maybe just from random outgassing. In theory, sure. If ice on the comet was concentrated in just the right spot, and if the comet happened to spin so that patch faced the sun at the perfect moment near perihelion, then maybe, just maybe, you get a push in exactly the right direction. Not impossible, but not likely. She wrote a quick memo, laid out the findings, and sent it to the Near-Earth Object Coordination Center. She added a note. This trajectory after conjunction deserved a closer look. Then she switched back to her other work. 2 days later, an email came in from a senior researcher at the center. They asked her to run more simulations, try out all sorts of outgassing scenarios, and see how often random jets could nudge a comet in just this way. So she did. 50,000 runs. She tweaked everything, rotation rates, ice patches, shapes. Each time the comet swung around the sun, random outgassing kicked in, and she measured the effect. Out of 50,000, 47 produced a velocity change within 10% of what they'd seen in 3IATLAS. Out of those, just 3 had the direction within 5 degrees of the observed shift, but not a single one matched both magnitude and direction at the same time. It wasn't impossible, just really, really unlikely. Her next memo spelled it all out. The numbers, the limits on the sample size, the messiness of modeling comets. She closed by saying the correction fit within what's possible for natural outgassing, but this specific direction deserved more attention. What she didn't write, what she really thought as she stared at the data, was that if she'd seen these numbers coming from a spacecraft, she'd call it a trajectory correction burn. A quick engine pulse, an intentional tweak. Someone at the controls. After conjunction, as 3IATLAS kept moving away from the sun, observatories everywhere kept a close watch. The object was gliding through a part of the solar system where Earth had a clear view and people were paying attention. Every few nights, telescopes in the US, Chile, Hawaii, Australia snapped new pictures, took new measurements, sharpened the trajectory even more. The path held steady. No extra pushes, no more sudden changes. The object just coasted outward, slowly escaping the sun's grip. As the weeks passed and new data kept coming in, the projected intercept with Jupiter's hill radius got sharper and sharper. By mid-February, the uncertainty shrank to about 20,000 kilometers. Early March, it dropped to 15,000. The object was locked in, a narrow path through space, a channel some researchers started calling the corridor. This was a precise slice through the solar system's gravitational landscape, leading straight to Jupiter's boundary. And here's the thing about the corridor. Once you're inside, moving at the right speed in the right direction, you're set. No more course corrections needed. Gravity takes over. It's like slipping into a river current. It just carries you along, shaped by the sun and Jupiter together. Getting into the corridor isn't easy. It takes a very specific position, a very specific velocity. But if you make it in, you're riding it all the way to the end. 3IATLAS was buried deep in the corridor, and the numbers just kept getting sharper. In March, after the talks wrapped up at a planetary science conference in Pasadena, a bunch of researchers ended up at the hotel bar. NASA folks, university types, some from private observatories. They all circled up, drinks in hand, and started in on the interstellar visitor threading its way through our solar system. At one end of the table, an MIT professor pulled out his laptop. He'd been running the numbers on 3IATLAS's path by himself. On his screen, he brought up a 3D model, the sun in the center, planets looping around it, and a fine line 3I/Atlas slicing through. The line swooped in from interstellar space, curved around the sun, and stretched out toward Jupiter. He zoomed in on Jupiter where a faint bubble, the hill sphere, showed the planet's zone of gravitational influence. The trajectory cut straight through the middle, right at the equator, threading the most stable patch. "So what do you make of it?" someone asked. "Natural or not?" The professor took a sip. "Honestly, I have no idea," he said, "and that bugs me more than if it were obviously one way or the other." A comet dynamics specialist from Arizona leaned in. "Here, what gets me," she said. "The timing. Perihelion lines up with conjunction. I know it's not suspicious, technically, perihelions when it's closest to the sun, and for certain orbits, that'll naturally overlap with conjunction from Earth's perspective. So the timing checks out if you're just thinking natural causes." "But," someone nudged. She shrugged. "But if I wanted to sneak a probe in for a course correction, I'd do it at perihelion 2. That's when you get the most solar energy. The comet activity's peaking, so any burn blends right in. And conjunction, that's when Earth can't keep a close eye. I'd hide the maneuver in the noise." Everyone went quiet then. Finally, someone from Caltech spoke up. "You know we can't put that in a paper." "I'm not saying we should," the Arizona researcher said. "I'm just saying that's what keeps me awake. The math works both ways. Could be a natural outgassing at perihelion just happened to nudge the trajectory, or something else. And I have no idea how to tell which." The MIT professor shut his laptop. "What we need is more data," he said low, "and we need to see what happens when it gets to Jupiter." But none of them knew, not that night anyway, that the perihelion maneuver during conjunction might not have been the only weird thing. Back in Arizona, at Lowell Observatory, a grad student working on something else had been digging through old images of 3IATLAS, shots from months before conjunction, and spotted something odd in the brightness data. Normally, comets brighten up steadily as they get closer to the sun. Sunlight bounces off their surfaces, outgassing ramps up, the coma gets bigger and more reflective. Sometimes you get a flare, sometimes a dip if it moves through its own dust, but overall it's a predictable pattern. 3IATLAS, though, showed a handful of brightness swings in the months leading up to conjunction, small bumps and dips that people chalked up to the comet's rotation, different parts reflecting more or less sunlight as it spun. But when this grad student plotted the brightness against its place in the orbit, she realized the changes weren't random. They lined up with specific points along the path. One of the brightest flares hit about 2 weeks before conjunction. She showed her advisor, who nodded and said it was interesting but not necessarily a big deal. Comets are messy. They flare, they fade. The brightness curve could be all about uneven ice or dust clouds or just the usual chaos of comet life. The grad student couldn't let it go. She kept staring at the numbers, pulling up images from other telescopes, checking if anyone else had caught the weird brightening before conjunction. Most observatories had aimed their instruments right at perihelion, so data from 2 weeks earlier was pretty thin. Still, a few readings from Keck in Hawaii popped up and they backed her up. There it was, a clear spike in brightness about 14 days before solar conjunction. The object brightened by around 15%, then faded back to its usual level over the next week. She tried running thermal models, hoping solar heating would explain the bump. No luck. The object was too far from the sun for a simple temperature jump to account for what she saw. Outgassing? Maybe, but comets usually do that much closer to perihelion, not this far out, not this early. She decided to check something else. How long did it take light to travel from the sun to the object's position during the brightening? About 48 minutes. Then, how long did it take the object to get from there to perihelion where conjunction happened? 14 days, almost exactly. That got her attention. She didn't write up a formal report. She wasn't sure any of it meant anything, really. But she saved her notes in a file called Pre-Conjunction Event and told herself to check back if anything else odd turned up. Meanwhile, 3IATLAS kept moving, drifting away from the sun, past Mars, past Earth, heading out toward the giants. New observations rolled in every few days. Every few weeks, the trajectory got a little sharper, the math a little tighter. And that point where it would cross Jupiter's Hill radius, that invisible line, 53 million kilometers out, stayed locked in, the uncertainty getting smaller every time. By April, the error margin was down to 10,000 kilometers. By May, only 5,000. The object was on track to pass through one very specific patch of space at one very specific moment. That kind of precision doesn't just happen. Not naturally, anyway. Maybe if everything lined up just right, a perfect launch, a lucky burst of outgassing at perihelion, or maybe something else was at work, something that didn't rely on luck, something that involved planning. Blind spots aren't just about what you don't see, they're about what can happen when you're not looking. Every security setup has them. There's always a gap somewhere. Astronomers have them too, times when you just can't get the data you need, no matter how much you want it. If something, natural or not, wanted to slip in a change without anyone noticing, those windows would be the perfect moment. Solar conjunction is astronomy's built-in blind spot. You can't get around it, and it's exactly the kind of thing someone clever could take advantage of. There's this thought experiment that comes up sometimes, late at night, after the conference crowds have thinned out. Suppose you wanted to send a probe to another star, and you wanted it to tweak its course when it arrived, but you didn't want anyone to spot that it wasn't just another rock. How would you do it? You'd make it look like a comet. Give it an icy shell so it throws off a coma and tail when it heats up. Make it big enough to be seen and tracked, but not so big that anyone can get a really good look. You plot a course that takes it close to the sun, because that's when comets get active, when outgassing is normal, when a little burst of thrust looks like just another part of the show. If you needed to nudge your trajectory, you'd do it at perihelion. That's when you have the most solar power, the most natural gas and dust to hide any exhaust. And maybe you time it so that, from the perspective of whatever planet you're trying to avoid, the whole maneuver happens during solar conjunction. Not because you're dodging their telescopes, they probably couldn't see your engines anyway, but because gaps in their data mean more uncertainty, and uncertainty gives you cover. All of this is just speculation, a mental exercise, not a scientific finding, but it's the kind of idea that sticks in your mind, the kind that keeps people awake at night. Because once you lay it all out, once you see how neatly 3IATLAS fits the pattern, it's hard to look at it like just another comet. Most scientists still call 3IATLAS a comet. Sure, it's a weird one, odd chemistry, a freakishly precise path, but it fits the bill for a natural object. Outgassing explains its perihelion acceleration well enough. The path toward Jupiter's Hill radius. Wildly unlikely, but not impossible. Space pulls this kind of trick all the time. That's the official story, and honestly, it makes sense. If you want to claim something extraordinary, you need rock-solid proof. So far, nobody found any. No strange radio signals, no alien alloys, no wild maneuvers that break the laws of physics. Everything we see, as odd as it is, still lines up with natural processes. Maybe we've just gotten lucky or unlucky, depending on how you look at it. But these little details keep piling up. Nothing huge on its own, but together, they start to paint a picture that's tough to ignore. Take the coma. Most comets spit jets of gas and dust from specific spots. You'll see the jets flicker as the nucleus spins. 3IATLAS doesn't do that. Its coma looks weirdly smooth, almost like someone airbrushed it. It's so uniform, you start to wonder if the outgassing is happening everywhere at once, or maybe not at all. Maybe we're just seeing sunlight bouncing off dust. Then there's the fragmentation, or actually the lack of it. When comets swing close to the sun, they usually crack up. The heat rips them apart, especially if they're new around here or not built very tough. But 3IATLAS, it sailed right through perihelion without so much as a chip breaking off. No splitting, no drama, just kept going. Its brightness is another oddball thing. Most comets flicker and flare, unpredictable as a cat in a laser pointer factory. Not this one. 3IATLAS has stayed steady, only changing as its distance from the sun changes, exactly what you'd expect if you ran the numbers in a textbook. It's almost suspiciously tidy. And then there's that photo. In November, an amateur named Paul Craig snapped an image with a backyard telescope. It made waves online because, for once, it showed something the big professional scopes didn't: actual structure. The big observatories, even Hubble, just showed a fuzzy blob, bright middle, hazy edges, classic comet. But Craig's image, all cleaned up with modern software, showed a shape. Not a perfect sphere, not obviously artificial, but solid, defined. And with this blue-white glow that didn't quite match regular sunlight. The argument started immediately. Some said Craig's image was just overprocessed, all artifact and no substance. Others argued small telescopes can sometimes catch things the big ones miss, especially when the big ones are busy doing something else. A few pointed out that a blue glow could mean certain gases, or maybe weird dust, and quietly some admitted the color and shape. They'd expect that from metal or ceramic. Nobody agreed. The image still sits in limbo, fueling the debate, but it's one more odd thing on a growing list. By June, as 3IATLAS drifted past Mars and into the asteroid belt, the buzz faded. Some scientists stuck with it, publishing papers on its makeup and its strange path. Most lost interest, moving on to whatever came next. The news moved on too. Another interstellar wanderer, interesting, sure, but not world-shaking. But a handful of researchers, mostly from the US but joined by folks in Europe and Asia, just couldn't let go. They kept watching, obsessively trading emails and video calls, sharing every scrap of new data. No official group, no fancy name. Someone jokingly called them the Hill Radius Watch, and well, it stuck. They decided to keep things simple. All eyes would be on what happened when 3IATLAS reached Jupiter. This wasn't just a routine astronomical event. It was a test. If 3IATLAS was nothing more than a drifting cosmic oddity, a stray visitor from the great interstellar beyond, then its path was already written by the laws of physics. It would cross into Jupiter's vast Hill sphere, that invisible domain where the planet's gravity dominates, feel a tug as it passed, and then continue its lonely journey out into the stars. Its hyperbolic trajectory meant Jupiter wasn't going to snare it. This was a fleeting encounter with a giant, not a capture. The object would simply remind us how much of the universe is still a mystery, passing by silently, leaving more questions in its wake. As everyone quietly wondered, what if there was more to it? What if this was no ordinary interstellar rock, but something else, something on a mission or perhaps following a plan? The Hill sphere crossing could be the moment the mask slipped. Maybe instead of a routine slingshot, the event would mark an arrival, the first act in a story we were only just beginning to read. The scientific community, fueled by excitement and a hint of anxiety, circled a date in red: mid-July 2025. On July 18th, 3IATLAS was set to enter Jupiter's gravitational domain, with its closest approach, just 53.4 million kilometers from the planet's heart, coming 2 days later, on July 20th. After that, the object was expected to continue on its way, unperturbed, fading into the cosmic darkness. Unless it didn't, and that possibility was the spark that set imaginations alight. As 3IATLAS entered Jupiter's gravitational sphere of influence, any number of unexpected things could unfold. Even though Jupiter's tidal forces are relatively weak at such a distance, far too feeble to shred a solid object, there was always the chance that 3IATLAS wasn't solid at all. If it was already fragile, perhaps a loose agglomeration of dust and rock, that slight gravitational pull could tear it apart. Debris would scatter, leaving behind a faint, ephemeral cloud that telescopes would watch as it dissipated, a ghostly signature fading over weeks or months. Astronomers would debate whether they just witnessed the demise of a natural comet or the unraveling of something more enigmatic. Alternatively, the object might remain intact, but something even subtler could occur. Non-gravitational forces, like jets of vapor from sun-warmed ices, should be negligible that far from the sun. Yet, if 3IATLAS harbored some hidden mechanism, some internal energy waiting for the right moment, a minuscule adjustment could shift its course. A tiny burst could decelerate it, causing Jupiter to capture it into orbit or accelerate it, sending it on a new, unpredictable path through the solar system. Such a maneuver would appear miraculous, but with no obvious cause, it would only deepen the mystery. Of course, there was always the chance that nothing strange would happen at all. 3IATLAS might glide through Jupiter's domain exactly as predicted, never deviating from its calculated path, leaving scientists with a textbook flyby and a lingering sense of anticlimax. In that case, the object would slip out of sight, leaving behind only data points and a new chapter in the catalog of strange interstellar visitors, a riddle unsolved, fueling speculation, but withholding any revelations. Preparing for every possibility, the Hill Radius Watch Group mobilized an unprecedented network of resources. They coordinated radio telescopes to listen for any artificial signals, infrared observatories to detect unexpected heat signatures, and optical instruments to track light curves and positions with relentless precision. For that critical week, the world's most sensitive eyes and ears would be trained on a tiny, distant object, hopping to catch any anomaly, however subtle. It was a demonstration of humanity's ingenuity and curiosity, a collective effort to reach across the void. Yet, even with this technological arsenal, uncertainty lingered. The absence of evidence did not mean the absence of action. A minuscule probe detaching from the main body, a barely perceptible change in trajectory, or a sudden dormancy, any of these could go unnoticed from Earth's distant vantage point. The object could complete its purpose, whatever that might be, and then blend seamlessly into the cosmic background, indistinguishable from the countless other rocks drifting through the solar system. This was the central, maddening dilemma. How could anyone distinguish between a natural wanderer and something designed to look natural? If 3IATLAS was crafted with skill, if its creators understood not only engineering, but also how to mimic randomness. Then every observation could be explained away as coincidence or natural process. Anomalies might be subtle enough to evade even the most careful scrutiny. The only definitive way to resolve the question would be to send a spacecraft for a close encounter, to capture images, analyze material, and search for unmistakable signs of artificiality. But no such mission was possible. By the time anyone could launch a probe, the opportunity would be lost, the object vanishing into the interstellar dark. So for now, all anyone could do was watch, hope, and speculate. The community would gather data, parsing every photon for meaning. But the odds were high that the true nature of 3IATLAS would remain forever out of reach. In the end, the universe would keep its secrets, and humanity would be left with little more than a tantalizing question, echoing through the years. Was it just another cosmic fluke, or had something extraordinary slipped past, cleverly disguised in plain sight? As the world waited for July 2025, the anticipation was as much about what might be revealed as it was about the mysteries that would remain. Late June in Mountain View, California, a SETI Institute scientist found herself mulling over an intriguing possibility. What if, just as 3IATLAS was passing through the hill radius, they used radio telescopes to listen for any signals it might be emitting? The suggestion wasn't rooted in a genuine expectation that the object was artificial. After all, the odds of intercepting a broadcast from an alien probe were vanishingly small. But the cost of listening was almost negligible, and the potential payoff, should they stumble on even a whisper of extraterrestrial technology, would be revolutionary. The risk-to-reward ratio was irresistible. Acting on this impulse, she quickly assembled a proposal, requesting precious observing time on two of the world's most sensitive radio facilities: the Very Large Array in the New Mexico desert and the Green Bank Telescope, nestled in the radio-quiet zone of West Virginia. Her argument was straightforward. This would be a rapid, opportunistic search, slotted alongside each observatory's regular schedule, so as not to disrupt ongoing science. Approval came in quietly, almost furtively. No press releases or headlines, just a discreet nod from the time allocation committees. Beginning July 15th, a network of radio telescopes would swing their great dishes skyward, tracking 3IATLAS as it arced across the sky. Their antennas would sweep a vast swath of the radio spectrum, from the most common frequencies used by human technology to those rarely monitored, all in the hope of catching something: a telltale electronic spike, an anomalous sequence of pulses, or even a faint carrier wave hinting at propulsion or guidance systems beyond current human invention. The prevailing wisdom was that they'd find nothing. If 3IATLAS was the product of engineering, it might use communication methods or spectral bands humanity hadn't even considered. Yet, history had shown that even unexpected discoveries sometimes came from simply paying attention. All the incoming data would be archived for posterity, ripe for re-examination as new analytical tools emerged. If anything anomalous surfaced, no matter how subtle, the team was primed to pounce, ready to dissect every bit. Meanwhile, the scientific response was blossoming in multiple directions. At MIT, a collaboration of astrophysicists and computer scientists was focused on extracting every hint of detail from the limited and often frustratingly blurry images captured of 3IATLAS. They were pushing the boundaries of image processing, leveraging the latest advances in machine learning. Their neural networks, trained on thousands of images of comets, asteroids, and even space debris, were now being unleashed on the sparse dataset of 3IATLAS. The hope was that a statistical outlier, a strange surface pattern, an unusual albedo, an unexpected symmetry might leap out from the noise, suggesting the object was more than just another lump of interstellar rock. Results so far were ambiguous. Some flagged features seemed promising, but the experts knew better than to trust unexplained anomalies at face value. Distinguishing genuine signals from image artifacts or algorithmic quirks was a painstaking process, demanding both skepticism and creativity. Across the country, at the University of Arizona, a different team was exploring the secrets hidden in polarized light. Polarimetry, the study of how light reflects and scatters off surfaces, could reveal subtle clues about the composition and texture of 3IATLAS, whether its crust was dusty and rough like a comet, metallic and smooth like a derelict probe, or something altogether unfamiliar. The researchers combed through vast catalogs, comparing the object's polarization signature to every known type of natural and artificial body. So far, the comparison yielded only puzzles. 3IATLAS didn't quite resemble any comet, asteroid, or even known spacecraft. Its peculiar way of scattering light hinted at an exotic chemistry, or perhaps a surface altered by processes no one had yet imagined. Each non-match only deepened the mystery, raising new questions about what kind of journey or event could produce such an outlier. At NASA's Jet Propulsion Laboratory, the scientist who had first flagged the odd perihelion acceleration was still intent on cracking the case. She had expanded her models, simulating an enormous range of cometary properties: ice distributions, jetting behaviors, rotational wobbles, feeding in thousands of random scenarios to see whether any could explain the trajectory shift observed as 3IATLAS rounded the sun. The verdict was clear. While not strictly impossible, the odds of natural outgassing producing the precise, targeted course change were exceedingly slim. Most comets that ventured into the gravitational grasp of giants like Jupiter emerged battered and redirected, their paths wild and unpredictable. None, in decades of data, had executed a maneuver as precise as 3IATLAS, correcting its course exactly during solar conjunction, then heading unerringly for a gravitational rendezvous. She scoured archival comet data, searching for even distant precedents. Had any comet, even by chance, pulled off a similar feat, altering its path with such precision at just the right moment to intercept a planetary Hill sphere? A handful of cases showed lucky breaks or near misses, but nothing approached the uncanny accuracy of 3IATLAS. The more she looked, the more the object seemed to defy classification. In early July, she set aside a morning to compose a new, exhaustive memo. This was no quick email. It was a meticulous synthesis of everything learned so far. She tabulated every trajectory measurement, laid out predictions and intercept calculations, and included rigorous statistical analyses comparing 3IATLAS's behavior with the entire known population of comets. She flagged the timing of the trajectory change, right at solar conjunction, when the sun masked the object from easy observation, along with the unusual shape of its coma, the unexpected polarization signals, and its remarkable stability against gravitational disturbances. Layer by layer, she built a case that 3IATLAS did not fit easily into any known category. The document grew into a comprehensive chronicle of the mystery, a timeline of oddities, a summary of negative results from radio and optical surveys, a set of theoretical scenarios, ranging from rare natural phenomena to the tantalizing possibility of artificial origin. She concluded not with answers but with a challenge. Here, assembled in one place, was the full suite of evidence. Something about this visitor was different. It was up to the global community of scientists, armed with new data, sharper tools, and perhaps a little luck, to unravel the truth behind 3IATLAS. The object was still out there, silent and enigmatic, as the world's instruments watched and waited for its next move. In the final section of her report, under a heading plainly labeled as speculation, she allowed herself to step beyond the data. All the phenomena we've observed from 3IATLAS can be explained by natural causes. But honestly, once you tally up all the strange details, the odds begin to feel off, and it's worth entertaining other scenarios. If this is an artificial probe, then what we're seeing actually fits. Perhaps it's exploiting perihelion for energy or propulsion, timing its maneuvers when the sun masks our view, or adjusting its trajectory to settle into a stable vantage point to observe us. Maybe it's even engineered to mimic the exact appearance and behavior of a comet, blending in with the cosmic background. I don't have hard evidence for any of this. But nothing here violates the laws of physics. We should keep observing, especially as it approaches Jupiter's Hill radius. That's when we need to watch for any deviations from ballistic motion, anything at all that doesn't fit the cometary script. She sent the memo to the Near-Earth Object Coordination Center, making sure to loop in a handful of senior colleagues she trusted implicitly. Then she waited, oscillating between anticipation and anxiety. 2 days later, instead of the usual flood of email replies, her phone rang. It was the director of the center, a veteran astronomer whose career had revolved around the study of comets and asteroids. He spoke with the calm of someone who'd spent decades peering into the dark and asked if she could join a video call later that afternoon. When she logged on, she was greeted by 5 familiar faces, each one a respected figure in planetary science, each quietly conducting their own investigations into 3IATLAS from different perspectives. The director got straight to the point. We have to decide how we'll respond if something unexpected happens on July 18th. For 2 hours, they hashed out every angle: observation protocols, data sharing contingencies, careful communication strategies. The consensus was clear. If 3IATLAS exhibited behavior that couldn't be reconciled with natural physics, if it performed a maneuver, transmitted a signal, or broke up in a way that hinted at internal architecture, they would report it openly but with measured language. No sensationalism, no conspiracy, just rigorous science, methodically communicated. But if nothing out of the ordinary occurred, if the object glided through Jupiter's Hill radius following the precise path predicted by gravity alone, then they'd publish their findings, catalog the oddities and statistical improbabilities, but refrain from making extraordinary claims. The scientific standard remained unchanged. Extraordinary evidence was required for extraordinary assertions. Without proof, it would remain simply an anomalous interstellar comet, one more puzzle among many. As the meeting wound down, the MIT professor who'd been experimenting with neural networks to analyze the data spoke up. "You know what troubles me most," he said. "We might never get an answer. 3IATLAS could genuinely be just a comet, or it could be something else, something constructed with such sophistication that it's indistinguishable from nature. If that's the case, if we're being observed by a probe that doesn't want to be discovered, then the very absence of proof might be the biggest clue we'll ever get." Not knowing, in a situation like this, starts to feel almost suspicious in itself. There was a pause. No one offered a response. The weight of uncertainty hung in the virtual room as they signed off, everyone returning to the business of preparing for the critical days ahead. Now, as mid-July arrives, 3IATLAS is less than 1,000,000 kilometers from the invisible boundary of Jupiter's Hill sphere. All over the globe, telescopes, both massive observatories and backyard setups, are fixed on a small patch of sky near Jupiter, tracking the faint, unwavering glimmer of a visitor from another star. Despite the sophistication of modern instruments, the object remains a mere point of light, barely distinguishable from the background static of the cosmos, its velocity a steady 27 kilometers per second. In just 3 days, that faint speck will cross an intangible frontier, a gravitational border defined only by mathematical models. Around the world, a quiet tension builds as astronomers await the moment, eyes glued to screens, searching for any sign, however subtle, that the object is more than it appears. Maybe its trajectory will remain constant, its light curve unremarkable, and the enigma will dissolve into the endless inventory of astronomical oddities, filed away and slowly forgotten. Or perhaps in that crucial interval, something will change. A sudden flare in brightness, a deviation in course, a fragment breaking away to reveal internal structure, Any of these could shatter the illusion of normalcy. If that pivotal moment arrives, the implications will be profound. We'll be forced to confront the possibility that we are not alone, that somewhere in the silent gulf between stars, another intelligence has engineered a machine subtle enough to traverse interstellar space, enter our solar system undetected, and perform its mission under the guise of a simple rock, a feat of technological artistry designed not just for stealth, but for ambiguity. The idea that something could be watching us, having come so far and hidden so well, would upend more than just astronomy. It would challenge our assumptions about our place in the universe, about what it means to observe and to be observed. And yet, perhaps even more unsettling is the prospect that we'll never know for sure, that 3IATLAS will pass through, leaving only questions and probabilities in its wake. The universe is vast and indifferent, and its secrets are not always offered willingly. For now, all we can do is watch, wonder, and record the faintest traces of possibility as a lonely speck of light continues its silent journey among the stars, carrying with it, perhaps, answers we are not yet ready to receive. That 40-hour window during the solar conjunction, that's the fulcrum, the moment everything might have turned. The trajectory didn't just nudge. It wandered, deviated in a way that left us poring over spreadsheets and telemetry, trying to find a reason that would settle the knots in our stomachs. The data's there, every decimal and timestamp, but the why, the engine of that change, remains a ghost, hovering just outside the reach of our models. Natural causes. Sure, the universe is full of surprises, outgassing micrometeoroid impacts, gravitational whispers from distant planets. Statistically, improbable doesn't mean impossible. Yet a tiny doubt lingers because sometimes the universe doesn't just surprise us, it unsettles us. You have to wonder, did something else act in those 40 hours, slipping across the cosmic chessboard while our attention was blocked by the sun, exploiting that moment when all our eyes were blind? Now we're on the threshold again. Another critical approach, another chance to watch, to capture every photon, every flicker. This time there's no solar shadow to hide behind. Our instruments are tuned, our algorithms sharpened, our attention laser focused. The world's observatories are aligned, synchronized, determined not to miss a second. But there's a humility that comes with distance. 3IATLAS is so far out, its signals are whispers in the cosmic static. Even with every scope on Earth pointed its way, we're still working at the edge of what's possible. The smallest shift, a probe splitting off, a low-power transmission, a course correction measured in fractions of a degree, could all elude us. We might not see it in real time, might only notice as the anomaly grows, as small discrepancies stack up until they're undeniable, until the story changes in retrospect. Space is a master of concealment. Sometimes the shadows come from physics, the sun's glare, Earth's rotation, the geometry of orbits that renders us temporarily blind. Sometimes the shadows are built into our machines, detectors not sensitive enough, software that filters out the unexpected, telescopes that can't follow fast enough. But the deepest blind spots are human, the expectations that guide our search, the assumptions we bring to every anomalous reading, the reluctance to see what doesn't fit. Our minds are hardwired for patterns, for explanation, for comfort in the familiar. But cosmic reality doesn't owe us that comfort. Since the moment we noticed it, 3IATLAS has been poking holes in all those blind spots. It's an interstellar visitor, not just a curiosity but a challenge, a test of how well we see and how honest we are about what we don't. With each new measurement we ask, do we understand what we're looking at, or are we still missing something? Some truth that slipped quietly past when our gaze was blocked. Maybe the decisive moment already happened, in that conjunction window, and what we're seeing now is just the unfolding of a plan we didn't even know was being written. The data's streaming in now, every observatory hungry for answers, every photon scrutinized by the Hill radius watch. Around the world, astronomers are holding their breath, poised between anticipation and dread. Were those 40 hours the moment of transformation, or just another gap in our vigilance, another fragment of the unknown slipping silently by? The next days will bring clarity, or maybe just deeper questions. Because in the cosmos, answers rarely arrive with certainty. Sometimes all we get is the hint of an answer, a pattern on the edge of perception, a mystery that grows more tantalizing the closer we look. Cosmic mysteries aren't puzzles waiting to be solved. They're invitations, challenges to our understanding, reminders that the universe is vaster, stranger, more complicated than we ever imagined. They linger, unresolved, and in doing so, they push us to see more, to think harder, to stay curious. That's the real purpose of the search, not to arrive at a tidy conclusion, but to remain open, to keep asking, to keep our minds lit with wonder even in the face of uncertainty. Right now, the search is alive. A tiny object from another star system is moving through our neighborhood, a relic or a messenger. Is it just inert matter, or is there something more, an artifact, a probe, a signal? It doesn't matter in a way. The act of searching, of watching, of refusing to look away is its own answer to the cosmic riddle. 3IATLAS reminds us that the universe is always moving, always hiding, always revealing itself in glimpses, never in full. Soon it will reach whatever destination it's been heading toward, long before we ever knew it existed. Maybe it will leave us with new questions, or a silence that speaks of all the things we failed to see. This time, we promise ourselves we won't look away. We won't let a blind spot steal the truth. But maybe the hardest blind spots aren't out there at all. Maybe they're inside us, the limits of perception, of imagination, of what we're willing to accept even when the evidence is staring us in the face. A rock that moves with intent, a pattern that looks too precise, a trajectory that echoes intelligence. Sometimes the truth is too strange, too unsettling, and we turn away, preferring the comfort of ignorance. In the end, maybe we're the blind spot. Maybe 3IATLAS has already seen us more clearly than we see it. And as it speeds away, it leaves us with a question more haunting than any anomaly. What do we let ourselves see? And what are we still blind to, even when the universe sends its mysteries right through the middle of our solar system? The answer, as always, is out there and within us.